audio. Start video. Oh, we've got a couple of students already. Thursday, October 15th. Strength of materials. We've got a good crowd. Ashley, Ben, Harris, Ben, Seaman, Braxton, Shane, Julian, Mohammed, Darren. We've got a good crowd. Do any of you have any questions for me? I guess not, huh? Well, let's see what we're going to do today. I think what we're going to do today is stress concentration factor. The topic for today is stress concentration factor. Unless you have a comment or question to begin with, the floor is open. Maybe we should remind you there's a test. I think it's made available today and it's due Sunday. Let me write that down. It's a take-home test. Of course, you're already home, so you don't need to take it home. It's exam 2. It's on chapters 3, 4, and 5. It should be available. If it's not, some of you out there, see if you can pull it up. And if you have trouble, I'll report it to my IT person. But I believe
Yes, I see it.
Did you pull it up okay?
Yeah, I can see it.
Good, excellent. It's due Sunday, I believe. Today's Wednesday. No, wait a minute. Yeah, that's right. No, today's Thursday. Yeah, it's due Sunday. That's right. I don't know about homework. Let me look and see if there's any homework. Today's the 15th of October. It looks like there's some homework too. You lucky people. The homework number 18 is 135. It's on page 255. And it would be due Sunday also. It's due Sunday also. Let me see if that page number is right. Page 255, number 8, 135. Yeah, that's right. Okay. All right. Well, we're going to talk about stress concentration factors. This is on page 242. And they're talking about shafts that have a fillet. See, here's a shaft. And one way of creating a shaft like this would be to weld two shafts together. Take a smaller shaft and a shaft with a bigger diameter and weld them together. But see, the weld would be right here. That's where the weld would be. And that weld has a radius. And this smaller shaft has a smaller diameter. This has a smaller diameter, D. And the larger shaft has a bigger diameter, D. And the weld has a weld radius of R. There's a picture of this on page 242. You can see it. And the way the equation works, see, it turns out the stress, you can tell by looking at this, that the stress is going to be bigger right there where that weld is. If that thing is going to have problems, it's going to be there where it's welded together. That makes sense. And it's called a stress concentration factor. And here's the equation. It goes like this. The maximum stress is going to be the stress concentration factor. Now we're talking about shear stress. You could put a little tau underneath that K if you wanted. And this would be, you could just call it the average stress. Now, obviously it's going to be in the smaller piece. So the average stress in that smaller piece we've learned is T rho over J. In fact, we have a name. We have a name for that equation. It's the most important equation in our chapter 5. Now let's see if one of my excellent students remembers that name. Alex, unmute and say hello, please.
Hello.
Hello. Alex, do you remember the name of this important equation right here?
The torsion formula?
You got it. It's the torsion formula. And we've learned what all these things are. That T stands for torque, which is an internal twisting. The rho stands for the distance from the center or the centroid. And the J stands for the polar moment of inertia. We've studied that. And so your equation looks like this. You've got this concentration factor, T rho over J. That's our equation. Now, how did they get this concentration factor? They have a name for it. You put a little taw there if you want. They call that the stress concentration factor. Stress concentration factor. How did they arrive at it? Well, they did it by experiment. They welded some of these together, and I guess they they stressed them. They put some external torsions on it. Here we go. And they increased it and increased it. And they discovered the thing would break. It would break right here. And they compared the external torsion with the external torsion necessary to break it here if you just had this small piece, and you'll discover it's takes a lot less. I think they just made a ratio. I really don't know, but these people they did it by experiment. That's the answer. How did they get this K? They actually measured the stress in some actual stepped rods. I guess you could call it a stepped rod. It steps step down. See, it's thicker here, thinner there, and now we have our equation. And you know you have some work to do for me. So unless you have a comment, we're going to work some problems. Anybody want to discuss what I've said so far? Well, okay. Let's work some problems. Now, this first one I want to work is 5.123. And it is on page, let me dig around here, I'll find it. It's on page 253. Okay, it says the shaft is used to transmit 30 horsepower. All right, well, let me make a note of that. We got 30 horsepower. You're probably going to need foot-pounds per second. So just multiply that by 550 foot-pounds per second is equal to 1 horsepower. Okay, well, let's get that. We're dealing with English units on this particular problem. Okay, I got 16,500 foot-pounds per second. That's our power. Now let me keep reading. I'm doing problem 5.123, 30 horsepower. Okay. It's turning at 600 RPM. Well, that's the angular velocity. It's 600 RPM. But you know what an RPM is? It's a revolution per minute. We don't want that. We want radians per second. So what you do is you go 2 pi radians is 1 revolution, and a minute is 60 seconds. And so now we'll get our angular velocity. They call this angular velocity. It will be and somebody out there double check me, make sure I'm doing this right. I'm getting 62.83 radians per second. Radians are dimensionless, so I'll just go 62.83 seconds to the -1. There you go. Now, if I didn't get that right, somebody speak up. Okay, now let me draw you the picture of this thing. We have a smaller shaft. And then we have this, we've welded it to a bigger shaft. There we go. A little artistic work there. Yeah. And we're going to transmit 30 horsepower. And turning, we read that. Find the maximum shear stress in the shaft. They're using a fillet weld. I think the way you pronounce that is fillet. But I hate to say fillet because I'm thinking of steaks then, as in filet mignon. Now the radius of the fillet is 0.18 inch. The diameter, that's the radius of that, but the diameter of this is 2.5 inches. And the diameter of this is 2 inches. I didn't exactly do that to scale, but oh well, maybe you'll forgive me. And they drew the external torsion going like this. So obviously there would be another one on the other end going like that. Now what do they want to know? Let me read this. They want to know the maximum shear stress. Okay, we can do that. If I can find where my pencil went to. I just dropped something, who knows where it went. There it is. You ever drop something and then it just disappeared out of existence? What's really bad is when you're working on your car engine and you drop a little part that you need and who knows where it went. Okay, well, we got a nice equation. It goes like this. The maximum shear stress is going to be that stress concentration factor do we know what the torque is? Let me read it. No, we don't. We don't know what that torque is. Do we know what that rho is. I think I can get that, and I think I can get the J, but we don't know what that K is either. But we have another equation that goes like this. For power. And see, we know what this is, and we know what this is. The power is 16,500 foot-pounds per second, and omega is 62.83 per second. So we can find the torque. I'm going to be quiet now for a minute. Here's an equation, and we know 2 out of 3 things. I bet you can get that torque. Go ahead, find that torque, and I'll call on one of my excellent students here in a minute. Well, let me call on somebody. How about my friend Ashley? Ashley, unmute and say hello, please.
Hello.
Hey, Ashley, have you plugged in the numbers and got the torque for me on this?
I got 262.61 foot-pounds.
That's what I got. 261.61 foot-pounds. Hey, looky here. We just figured this out.
I got 262.61.
So did I, Ashley. I don't know why I wrote that one there.
Okay.
You're absolutely right. Give you a small, skinny thank you point, Ashley. There you go. Keep me honest. Don't let me get away with anything here. Well, we're making progress. Now this row here, you know what that's going to be? That's going to be the radius. This small thing is going to break off, and we need the radius there. It's just 1 inch. I got room right here. That'll work. That row is just going to be 1 inch. Ta-da! And we know what that row is. Now the J, well, we're talking about the polar moment of inertia of this smaller diameter rod. So it's going to be pi over 2 r, which is 1 inch to the 4th. I can handle that. Hang on, let's see. Pi over 2. That's it, because you just have 1 to the 4th. I'm getting 1.57 blah, blah, blah inches to the 4th. The units for the polar moment of inertia in this case are inches to the 4th. So look here, we got that too. You know what? If we could only solve for this stress concentration factor, we would have our answer. Okay, well, to do that, you have to look at this graph. A lot of things in the real world are reading graphs. Not everything has this nice algebraic formula. There's some things in the real world that they measure it, and then make a graph. And this graph is made from actually measuring different step down rods, stepped rods. Okay, so what we need to enter this graph, and it's on page 242. Now I need some room to do this. We'll make us some room. Here's some room right here. First of all, I need R over D. R over D. That's the radius of your weld, which is 0.18 inches. And D is the small diameter, which is 2 inches. I can do that in my head. Time to show off a little bit. I'm getting 0.09 nothings. You know what? Inches over inches. The units go bye-bye. 0.09. Great. But we also need something else. We need big D over little d. Big D over little d. Now, big D is 2.5 inches. And little d is 2 inches. Is it 1.25? I don't trust myself. I think it's 1.25, but let me make sure. 2.5 divided by 2. Yeah, that's right. Nothings. It doesn't have units. These are just ratios. Okay, now we're going to enter this graph. Now, I'm talking about a graph. See where my thumb is wiggling there? There's a graph in your book, and it's on page 242. And I'm going to enter the 0.09. Okay, well, that's in between 0.05 and 0.10 and 0.09. All right, well, I think I found it. And then I have to go up till I get to this D, big D over little d. It's 1.25. Okay, hang on a minute. Let me see if I can find that. 1.25. Yeah, I see where it is. Okay, guys, I think I know 0.09. There it is. Dang near 1.35. I wonder, does anybody agree with me that the K is 1.35? If you agree with me, say, uh-huh.
That's what I'm looking at.
Does that sound okay?
Uh-huh.
I bet that's right. 1.35. All right, well, let's put it in. Here goes. I just need some room to put that in. So we got 1.35. We figured out the K. And the torque is 262.6 foot-pounds. And the rho is 1 inch. And J, dang it, did I erase it already? Oh, heck, I think I erased it. I know that's it, because I recognize the units. See, J is in inches to the fourth. I think my J is 1.5708 inches to the fourth. Now this is going to give me the maximum shear stress, and it's going to occur where that fillet is. That's where the thing is going to fracture. But there's units. If you just plug those numbers in, you won't get the right answer. Here's what you have to do. You have to go 12 inches is a foot. You have to do that and to get rid of those feet. See that foot right there? That foot will cancel with that foot, but you can't leave that 12 out. Units are important. If I don't teach you anything else, I would like it for you to know that units are very important and to know how to make them the same on both sides of an equation. See, you got inches times inches divided by inches to the fourth. Well, that gives you square inches per square inches. You have pounds per square inch, and that's what you want, because stress is in pounds per square inch. Okay, we're going to plug this into our calculators now. Get your calculator, plug that in, and then I'll call on one of you, and we'll see how we did. Here goes. Well, I got an answer. Let me call on somebody. Let's see. How about my friend Ben Harris? Ben Harris, unmute and say hi, please.
Hey, how's it going?
Yeah, terrific. It's kind of cooled off that north wind. So there are going to be a couple of cooler days, I think, Ben. Ben, did you plug that in? Did you get an answer for the maximum shear stress?
Let's see. I've got. Let's see. I'm punching it in right now.
Yeah,
I'm
take
almost.
time. Other people are punching it in too.
I've got 2,708.35.
2,708. We'll just quit there. That's good enough. Now, Ben, what are the units?
Let's see. That is going to be. So foot-pounds per inches cubed.
No, we got rid of the foot, Ben.
Oh, you're right. Yeah. Let's see. So that's going to be. So pounds per inches cubed.
You're darn near. You're awfully close.
Or inches.
Pounds per inches squared. So you got inches times inches,
Okay.
and you're dividing by inches to the fourth. So it's pounds per inches squared. You know what that is? That's a PSI. Now let's look and see what the answer book says. Go to the back. We just did 5/123. And let's see what the book says. 5/123. Book says 2.76 KSI. The book says 2.76 KSI. Well, I didn't get that. I got, if you made that KSI, it'd be 2.71. Wonder why we,
Professor?
oh, I know what it is. It's reading this K on the graph. See, the book answer is pretty much the same as ours. But when people read graphs, You're trying to read a graph, and it's possible. It is possible. Let me look at this graph again. Our answer might be as good as theirs. It looks like the K is, if you're careful, is a tad bit bigger. Instead of 1.35, it's probably more like 1.37. That was a little bit sloppy. A more careful reading of the graph, I believe, would give you 1.37. Well, now let me do that and see what I get. Here goes. I'm going to do that. See if we can get closer to their answer. But they're not perfect. They can be wrong too, you know. Okay, I'm getting a 2.75 KSI, which is a little closer to their answer. I think their answer is better than mine, our first answer. I think I was a little bit sloppy on reading that graph. How about you guys? You agree with that?
Mr. Griffin,
Yeah.
how are you getting that K value? I mean, how are you reading that graph? Can you show that one more time?
Yeah, let me show you on that graph. I need to make some room here, Mohammed, and I'll show you what I think about that graph. What we wanted was 0.09. Well, they have a 0.05 and they have a 0.10, and they have these lines here, and they have .06, .07, .08, .09. There we go. And what we wanted was 0.09, 0.06, 0.07, 0.08, 0.09. We want this one. You know what? This is 0.09 right here, isn't it? I think I did it wrong. I think I went in between these two. I was thinking that's 0.08, but it's not. So we got to go up. We're going to, Mohammed, we're going to go up this line here. Now they have these other things swooping down, and we wanted a 1.25. Okay, I see. It's the next to the last one. It's kind of going like that. Yeah, maybe not that. I think that's the bottom one. I think what I want's the next one up. And here's what we want right there, where this one is the 1.25. So you come over here and you read the K value. And it is, let me get my sharp pencil here, 0.09. You know what? It's more like 1.375, isn't it? Yeah. I was a little bit off. 1.375. Mohammed, the correct value should have been 1.375. And I bet you'll get a much closer answer to the book. The book probably did a good job on that. Did that make sense, Mohammed?
Yes, sir. Thank you.
Yeah, anytime. Okay, well, that was fun. Let's do another one. Let's say goodbye to that problem. We're going to do another one now. Today we're studying stress stress concentration factors. Actually, what it is shear stress concentration factors. That's what we're studying. Now this problem here is 5.122. Let's see if we can do it. It's on the same page. It's on page 253. We could go ahead and get let's get that stress concentration factor now. But we need that R over D thing. R over D. On 5.122, the R is, well, it'd be 30 millimeters, you know it? The diameter is 60, so the radius is 30. And now here's where I'm getting confused. They have an R over D. No. That's not right. The R is the radius of the fillet, which is 0.18. No. 13.2. 13.2 millimeters is the radius of the fillet, and the smaller diameter is, what would be 30? So this little R over D is equal to 13.2 divided by 30. I'm getting 0.44.
Would the D be 30 or 60?
Uh,
I thought 30 was the radius of the smaller.
You know what? I think I'm going to owe somebody a thank you point. It's a diameter. It's a 60. Now, who was it that I just talked to? Who is that?
This is Alex.
Alex, you get a big honking thick thank you point right there, Alex. Good going. This is wrong. Thanks to Alex, we're going to get this problem right. 13.2 divided by 60 is 0.22. Okay, now we also need the business of big D over little d. All right, well, we can do that. Thanks to Alex, we know little d is 60 millimeters. But what's the big D? Well, it looks like 100 millimeters. Let me do that. Okay, 100 divided by 60. I get 1.66, a whole bunch of sixes. Okay. Now let's go to our graph. Find 0.22. Well, I see the 0.2. I see where 0.22 is. 0.2, 0.21, 0.22, 0.23, 0.24, 0.25. There it is. I found it. Now we're going to go up to 1.667. It's the middle one, isn't it? It's the middle one. So I'm going to go up to, hey, you know what? It's 1.2. Do you agree with me? 1.2. I'm waiting for an
That's what I see.
I think that's right. Okay, now we're going to find the Oh, now wait a minute. They want the power. They want the maximum power that you can transmit without breaking this thing, without it fracturing. Well, you know the equation for power. It goes like this. Do we know the omega? Yeah. Yeah, we can get that. I mean, it's given. And if we could get this torque, this is given, we could find the power. Now let's see if we can get the torque. Well, this equation here says, this is called the Fletcher formula. They're going to give you this. They're going to give you, you can only have 150 megapascals. They're going to give you this. And we know what this rho is. It's going to be the small diameter, that little d thing. And I think we can get that. Hey, we can get this torque. That's supposed to be a T there. We're going to plug it in here. We're going to find the power that this thing could transmit. Okay. Let's do this. Now they said, I need some room. Yeah, we did all that. I'll make some room here. They said you can only have 150 megapascal. That's as far as we're allowed to go. Something bad happens after that. We're going to solve for the torque. Now the rho is going to be 30. 0.030 meters. And J is pi over 2, 0.030 meters to the fourth. Okay, I want you to solve. I'll be quiet for a minute. I want you to solve for the torque. Go for it. Solve for the torque.
Professor, isn't that radius 0.06?
Say that again, please.
Isn't that that rho 0.06 meters?
Hang on. No, that's the diameter. The rho is the radius.
Radius, okay, that's why it's 0.03. Okay, thank you.
Anytime. But see, that's how you get thank you points. You have to stick your neck out a little bit. You didn't get one this time. Tell me your name.
This is Ben Harris.
Ben. Yeah, thanks for trying, Ben. You keep trying. Okay, well, let me call on one of my excellent students here. How about my friend, since I was just talking to Ben, do you have, well, he's still changing the number there. Ben Seaman. Ben Seaman. Can you unmute and say hello?
Good morning.
Yeah, good morning. Hey, Ben, did you solve this and get the torque?
So do we not use the stress concentration factor at all in this equation?
Wait a minute, Ben. You know what? I think he might get a honking thank you point out of this. I think I'm forgetting it, aren't I, Ben? Bless you. I need to put a K in here, don't I? Oh, no, wait a minute. Yeah, I do. I definitely do. I forgot all about it, Ben. So let me do mine over again here. All right. I think I have what it is. Ben, using the, This is Ben Siemens honking thank you point right here. He's absolutely right. See, the equation goes like this. The maximum shear stress is equal to this stress concentration factor there's the equation, and your instructor, that's me, forgot all about the K there. But thanks to Ben, we're back on track. Ben, did you have time to figure out the torque in this equation?
I got 5,300.
That's what I got. So right now, thanks to Ben, we have I got 5301. What would be the units on that, Ben?
Would that be Newton meters?
Yep. Newton times meters. Don't ever let me catch any of you saying it's newtons per meter, because that's wrong. Torque is newtons times meters. Just like torque is foot-pounds, feet times pounds. They're not feet per pound or pound per feet. You could say pound feet, that'd be okay. That a pound foot's the same thing as a foot pound, but you don't divide them. Okay, good going. Now let's see what we got now. I got lost, I forgot what I was doing. Got all carried away about my units there. See, units are just so terribly important. Oh, here's what we're going to do. We're going to find the power. Now we know the torque. Let's write it out. It's 5301 newtons times meters. And the angular velocity is, read the problem. It is 450 RPM. But see, what you have to do, let me make some room here someplace. I need some room. This will work. We need 450 revolutions per minute. You got 2 pi radians per revolution. And a minute is 60 seconds. So you take 450 times 2 times pi divided by 60. I'm getting 47.12 radians per second. Nothings per second. And that goes here. 47.12 radians per second. And we'll have our power. Okay, do that. 5301. Well, I'm getting a humongous number, but I can't help it. I'm getting a 249,804. But what are the units? They're Newton meters per second. Did you know we've got our very own special unit for power that's equal to a Newton meter per second? Does anybody know what it is? The unit for power.
The watt.
It's the watt. See, a Newton meter is a joule, and a joule per second is a watt. A watt is a joule per second. And of course, a joule is a Newton meter. And so a Newton meter per second, that's what we got. We got Newton meters per second. So we have watts. Now, the answer book will probably say, they'd probably round it off. I bet they'll say 250 kilowatts. Now let's look up the answer. This is 5122. Go to the back of the book and let's dig around. Let's see if we can find it here. 5122. Yeah, they rounded it off. That's exactly what the book has. The book has 250 kilowatts. Okay, well, great. We got that under our belt. And we still got a half hour. We could even have more fun. We probably ought to do something else, so I'm kind of bored with this concentration factor jazz. Did you know we skipped this, the section on normal stress concentration factor? Let's go back and look at that. I wonder where it is, though. I don't know if I can find it. Help me find. Let me shop around here just a minute. Concentration factor. I don't know where it is. Tried to find it in the index, but I know it's got to be back here someplace. Yeah, here we go.
Is it in chapter 4?
Yeah, it's chapter 4. You're right, and it's on page 164. Let's talk about that. They have fillets and holes, is what they have. Let's just do the holes. I need some room here. And now I'm on page 164. And we're going to study normal stress. See, what we just did was shear stress. But right now, we're going to study normal stress concentration factor. And here's how the equation works. This stuff all builds, and this won't hurt you a bit to review some basics here. That's the symbol for normal stress. And it's just equal to the normal force over the area, right? Only here, they're going to talk about a concentration factor. They should have an equation like that. Let's see if they do. Yeah, there it is. Well, they wrote it kind of funny. Here's how they wrote it on page 163. They said this concentration factor, you could put a little sigma underneath it if you wanted, is the maximum normal stress divided by the average normal stress. Well, see, the average normal stress is just the normal force divided by the area. So you can see where I got this equation. Now, this equation here is for your maximum, and they have two things that can cause an increase in stress. One of them is holes, the other one is fillets. Well, we just talked about fillets a little bit. Now you can pronounce that fillet as if you want. But one of them is holes. Now, they put holes in things for a variety of reasons. like in an aircraft wing, did you know they have holes? For several reasons. One is they can run cables and wires through those holes in the wing, and another one is those wings are filled with aviation gas, and you need the gas to be able to flow inside the wing there. And it makes it lighter. See, it's just as strong, but it makes it lighter. But whenever you have a hole, it does weaken it. And they've measured the increase in stress with a stress concentration factor. Let's do an example. Suppose you had a rod like this. We're just going to make up an example. Suppose this is, I'm making this up, 1 inch by 2 inches, okay? It's 1 inch wide and 2 inches tall. And let's put a force on it. And I'll just make up a force. Suppose you have I'm just making this up. 1.5 kips. 1.5 kips. And suppose you have a hole right here. Artist rendition of a hole. And suppose the diameter of that hole is, I don't know, 3/8 of an inch, let's say. I'm making all this stuff up. Now, if you stretch that piece, where do you think it would break? My guess is it'd probably break where the hole is. Does that make sense? Because it weakens it. Obviously, it's going to break where that hole is. It's going to have a stress concentration factor. And they've measured that for a lot of different rods with holes in them. And let's find out what it is. But we're going to find out what the K is in this equation. Now to do it, we need 2R over W. Now the R refers to the radius of the hole. Now 2R would be the diameter of the hole. So 2R is 2 times the radius of the hole. That's what the 3/8 is. That's the diameter of the hole. And the width, that's this 2 inches here. So this is equal to, get your calculators. I can't do that in my head. But it's going to equal 0.1875. And if I'm wrong, you sing up. Now, we have to go to this graph. I'm on page 164, and what we're talking about now is normal stress concentration factors. So you can put a little sigma underneath that K. It's a normal stress concentration factor. And what I need is 0.1875. Well, let me see if I can find it. There's 0.1. 0.1246. Yeah, there's 0.8. 0.1875. That's pretty close to 0.19, isn't it? Yeah. Well, I tell you what I think, guys. I think it's between 2.425 and 2.45. It's kind of hard for me to estimate that. What's halfway between 2.42, just a minute, 2.42 and 2.50? I think that's where I'm at. Well, I'll tell you what it'd be 2.46. If I did that right, the normal stress concentration factor is 2.46. You guys stare at your graph and see if you agree with me. 0.1875. Yeah. Yeah, that's about right. 2.4. You think? Yeah, that's about right. Okay. So the maximum normal stress is going to be 2.46. See, that's going to increase the stress, and it'll cause failure, obviously. And now we need this normal force, which is 1.5 kips divided by the area. Now, what area are we talking about? Well, it's this area here. See, there's a hole there. Let's see if this makes sense to you. And what's holding this thing together is this area here, because the hole is there and there's no material there, it's just empty. That area is equal to, what's 2 minus 3/8? One and 5/8? I wonder if I did that right. If you take 2 inches and you subtract 3/8 from it, do you get 1 and 5/8? I think you do. Times 1. See, that's the area that's holding this thing together. Okay, do that with me and tell me what the maximum stress is in this example piece that I just did for you. Go for it. Well, I got an answer. How about you guys? Anybody got an answer yet on that? Let's speak up and I'll put it on the board. Well, let me call on somebody. How about my friend Brian? Brian, I haven't called on you in a while. Unmute and say hello, Brian, please.
Hello.
Hello. Hey, Brian, have you plugged this in and gotten the maximum stress in this piece?
Yes, sir. I got 2,270. Sorry, 2,270.
Say that one more time, Brian.
I got 2,270.
That's what I got.
Okay.
That's what I got. I got 2,270. But what's the units?
Would that be what do you call it? Would that be pascals?
Brian, turn up your volume, I guess. Or either that or I need to get a hearing aid.
I don't know. I'm sorry, my laptop microphone isn't very good. Would that be pascals?
You're not going to have pascals. If you said pascals, forget it. This isn't metric. This is English, senor.
Oh, okay.
So it's not
PSI?
pascals. What is it?
Is that PSI?
Yeah, there you go. It's PSI. Good going. Okay, well, hey, let's we got time. Let's do one in the book. Now this is problem this is problem 487. Yeah, that'll be fine. Okay, let me erase all this. And we're going to do, the topic today is concentration factors. And what they've got there is a rod. Now this one's a stepped rod, but we can do it. We can do it. Artist's rendition here of the stepped rod. And they've got a little radius of curvature there. We're going to have to use the fillet and the hole. There's a hole here. This distance here is 40 millimeters, and the radius of the hole is 20. No, that's the diameter. The diameter is 20 millimeters. The radius of the fillet is 10 millimeters. And this dimension here is 20 millimeters. And it's 5 millimeters wide. Well, let's do the hole first because we've learned how to do that. And now they're going to put 8 kilonewtons on it. Here, let me do that. Okay, let's do the hole first and then we'll do the fillet. And we'll see if we can get this one right. Okay, go back to the business about the holes there. And I need 2R over W. Well, see, that's the diameter. 2 times the radius is the diameter. So it's 20 millimeters over 40 millimeters. Isn't that what the W is? Did I do that right? Yeah, I did that right. Well, that's 0.5. I can do that in my head. There we go. All right, find the 0.45 and You go up and you know what it is? It's 0.21. The stress, not 0.21, 2.1. The stress concentration factor is 2.1. You have to be on page 164 to get that. Any question on that so far? All right, now I haven't shown you how to do this fillet business, but we're going to do it now. You need a little r over h. Well, little r over h is 10 millimeters over well, it's over 20 millimeters, isn't it? I'm getting 0.5 for that. Did I do that right? I think so. Yeah. Yeah, I think I did that right. But now on this fillet, you've got to be on page 164 to know what I'm talking about. We also need r over h. No, I mean w over h, the width over the height. Okay. Well, let's see, the width is 40, isn't it? And that h is that h is 20. I'm getting, that's equal to 2. Now we're going to read the concentration factor for this fillet. See, here's the thing. Will it break at the whole? It's weakened there, or will it break at the fillet? It's weakened there. One of these is going to break. Well, we're going to find out which one. That'd be interesting. All right, find this 0.5. I found it. Go up to where it's got a W over H of 2. And I see it right. Oh gosh, you gotta have good eyes to see this stuff. And I don't. That's a big problem. Yeah, I think I see it. And what we need is we need 0.5. Got that. And we're going to come up here where it says 2. Yeah. All right, I think I see, yeah, I think I see it. Okay. Man, I'm having trouble reading that. But you know what? I think it's 1.4. I think it's 1.4. For the fillet, the normal stress concentration factor is 1.4. For the whole, the normal stress concentration factor is 2.1. All right, now we'll write our equations. Here goes. Now I lost track of what problem we're doing. We're doing problem 487. It's on page 172. Determine the maximum normal stress developed in the bar. Well, for the whole, the maximum normal stress will be 2.1, 8 kilonewtons divided by, and here's where you need that area here again, remember? That's holding it together. And I tell you what that is, that's 40 minus 20. Well, it's actually 0.0440 minus 0.020 times 0.005. That's the thickness, and that's how much you got there, because you have to subtract the whole, right? You got to subtract the whole. Somebody do that. Now for the fillet, here's what you'll have for the fillet. The maximum normal stress for the fillet is going to be 1.4. That's what I got. Nobody said anything, so it might be right. Times 8 kilonewtons divided by this cross-sectional area here, which is 0.020 times 0.005. Now this will tell the story. That's supposed to say meters there. This will tell the story. The big one, whatever the big one is, the maximum stress, isn't that where it's going to break? I would think so. It's going to break where the stress is maximum. Oh, gee. It's sad, but I'm running out of time here. The answers are in the back, though. It's 487. You guys could finish this on your own. It's 487. And one of these answers, I don't know which one, they said is 168 megapascal. If we only had time, we would do that, but we don't. We're out of time. But that's how you do it. And now we've studied concentration factors, and you know that you have places that have they're weaker, and they'll break there. The stress goes way up. Okay, guys, we're going to have to adios because I've got another class. Any last comments? Better say them now. Okay, well, bye-bye till next time. I'll see you on Tuesday morning at 9:30. Bye-bye, students.
Have a good day, Mr. Griffin.
Bye.
You too. Be
Have a good
careful.
weekend.